Yeah.
No.
Look, I was gonna say shave it. Look. It's a video. It's so weird.
You been down there?
How do you know I gotta wear hats?
I haven't like been. I've been like.
I think I actually has that ground for.
Like, I was so happy, like, I wanted to hear her voice and I really knew what I was saying.
All right, let's look. Let me go over your packet here. So yesterday, we went over a big topic, solving differential equations. We worked through pages 1 and 2, all the examples on both pages. Encourage you guys, for those of you who weren't here, encourage you guys, for those of you who weren't here, to watch the video that I recorded and I uploaded on the website, just going through each of the steps for solving equations, solving these differential equations. We're going to do a little bit of it today, but today is more geared towards solving these types of word problems, which has not as much calculus involved. We're really just practicing taking that information, organizing it, and finding missing variables and solving for what we need to find for the problems. If you go to page 3, these are the summary of steps that I highlighted as we're working through the problems from yesterday. So just want to kind of refresh our memory with what we covered yesterday, and we'll definitely do a lot more solving differential equations next week. Okay, as we prepare for the test, but no test next week, it'll be the week after. So rewrite, whenever you see y prime, you always want to rewrite this as a more descriptive form, like for instance, dy over dx. Okay. Now you're going to see that it could be either dy dx or it could be dy dt. For now, all of the variables that we're dealing with have been x's and y's. So you'll see it as dy over dx. Sometimes if a problem gives it to you where they give you that differential fraction, okay, they give you that differential fraction, but the variables are not familiar, then look at where they're located. Okay, so basically anything that is in the numerator is going to tell you what the dependent variable is. Whatever variable you see in the denominator is going to be the independent variable. So if you see dy over dx, you know that x is going to be the independent variable and y is the dependent variable. If you see dy over dt, you know t is the independent variable and y is the dependent variable. Okay. We talked about yesterday how the first thing we want to do is to be able to group the dependent variables together on the left side, the y and dy, and then the independent variable we want to group on the right side of the equation. So x and dx, or later on we're going to see t and dt as a popular independent variable as well. We like to start by cross multiplying equations to rearrange our variables in the numerator. So when we cross multiply, we may not get full separation, but we will ensure that our dy and dx are locked into their right spots, right? We need the dy and dx to be in the numerator location, and then from there we decide what else needs to be moved to get everything in their proper places. Okay? It's okay to have variables x or y in the denominator after the variables are separated. I think part of what I see in the past is sometimes students see the variable in the denominator and they're not comfortable with it, so they end up moving it to the numerator, and it ends up being the wrong the starting spot for the antiderivative. So hopefully after you do enough problems, you'll kind of just algebraically kind of trust that process, and wherever it ends up is where it needs to be when you take the antiderivative. Sometimes it could be the numerator, sometimes it's in the denominator, but let the algebraic steps lead you to it. Don't just assume whether it's one way or the other. Okay. If parentheses are presented in the differential equation, go ahead and keep them, right? The parentheses are there to help you separate and group what needs to be grouped together. I know that when we're dealing with power rule problems, I always said expand everything out so that you can do power rule. But in this case, we have multiple variables involved on the same side, so we do want to keep the parentheses to hold on to that. If we lose the parentheses, we kind of take a step backwards in terms of the progress that the problem is trying to help us with. And then this is more of a minor point for number 9, is to try to keep the left side of the equation as minimal as possible. Sometimes we can't move the coefficient or the numeric values to the right side because it's stuck inside that form, but easier problems where that coefficient is just being multiplied, if we can move it to the right side, we want to go ahead and do that. It just ensures that the left side is a little bit cleaner, a little bit easier to work with, because ultimately, whatever coefficient that's on the left side, eventually at the end has to move over to the right side as well. So the little steps that we can take at the beginning will just make things a little bit cleaner and easier down the road. Okay, so let's go to page 5. We're going to do a little bit of practice with solving a differential equation, but our focus after that is mainly going to be using that equation to solve missing variables. Okay, if you have your calculator, go ahead and have those out. Okay, let's start off with definition here. Direct proportion equation is one that looks like this, where we have y is equal to kx. It's in this form. Whatever variable is presented to you on either side of the k value, they're all sitting in the numerator. So direct proportion just means that when y is increasing, x is also increasing by some constant. And if y is decreasing, then so is x as well. So k is called the constant of proportionality. Inverse or indirect proportion equation, we're not going to see this as much, but this is in the form of y equals k over x. And this ensures that when y is increasing, x is decreasing, and vice versa. They're both going to be going in opposite directions. Okay. But mostly what we're going to see today are just direct proportion equations. Okay, so number 1, it says if the rate of change of y varies directly with the value of y, find the general equation. So what we're going to do is we're going to translate this sentence into a differential equation, and then we're going to solve it. Okay, so first it says rate of change of y. So rate of change of y, let's treat that like the derivative. So we'll call this representing y prime. Varies directly, so we know it's going to, direct proportion is the form that we're after. So we know that y prime is equal to k times, and the sentence should tell us what this last variable is. And it tells us it varies directly with the value of y. So that is the variable that comes after k, so k times y. Okay. We have a differential equation in front of us. We're now going to solve it and we're going to bring it up to the general equation level, get it out of the derivative form. Now, y prime, we can treat that like y as dy over dx, which is fine, but we're heading into the direction of these word problems where time is the independent variable. So let's just think of that y prime as dy over dt. Okay, now the right side, let's go ahead and get it ready for our next step. We want to cross multiply because eventually we want all the numerators, our dy and dt to be nicely separated, to be in their right spots. So I'm going to cross multiply here. So I have 1 dy equals to ky dt. Okay, so one of the first things I want you to notice is look at the progress we've made here already. dy and dt are on the opposite sides of the equation, and they're in the numerator. Dy is on the left, dt is on the right, dependent on the left, independent on the right. So at least we know these two are in the right places, okay? So now the next question is, do we have full separation of variables though? Is there anything out of place still? It's that y, right? So we want that y to be over on the left side with the dy, and how do we get it there? Divide, okay? So when you divide by something, it's going to usually end up in the denominator. So it's okay to have that y in the denominator if algebraically that's where it tells us to go. Okay. We know the y is going to be gone from the right side. And we talked about how we only want what's on the left side, what is absolutely necessary. So only the y and dy is needed there. The k is a constant. We're going to leave that on the right side. We're going to just push just what's needed on the left side. So we should have full separation now. Let's go ahead and set up our antiderivative. So I like to write it this way, with the dy a little bit on the outside to the right. So 1 over y, not dt, dy. K is a coefficient, so technically we can push it outside the integral because it's not really involved in the integral process. Now, you don't see a number involved here for dt, so I like to put a 1 dt as a reminder that I'm really taking the antiderivative of 1 with respect to time. Okay, so everything is separated, everything is ready for our antiderivative rule. What does the integral of 1 over y turn into? Yep, natural log absolute value of y. There's a plus c, but we're going to save that plus c to show up on the right side. Okay, the k is just going to tag along to whatever the integral is. What's the integral of 1 dt? Okay, but you have the right idea, but here the dt tells us that the independent variable is time. Yeah, so just t, so kt plus c. You have the right idea. We're going to kind of move towards variable t, especially with word problems. Okay, any questions so far? Okay, so we're done with the calculus. We moved everything up to the function level, but we still have one more thing to take care of and to try to get that y out from under that natural log. So how do we get that natural log to be e? Yep, we're going to involve the inverse function. We know inverse of natural log is e. E and natural log have a way of kind of undoing or canceling each other out. So whatever we do to one side, we ought to make sure we do to the other side as well. E and natural log handles each other. We're left with absolute value of y. We can let that drop down. And we're left with e to the kt plus c. Remember that this kt plus c, they're all sitting at the exponent level. Yesterday, we talked about how we wanted to get that constant away from the rest of the variable so we can have an expression for that. We talked about yesterday how we can use an exponent property. If I have a to the n plus n, I can separate that into a to the m times a to the n. So the addition of exponents is going to turn to the multiplication of bases. So how can I get that e to the kt plus c to be separated using this property? Okay, but not plus. It's going to be what? Times. Yeah. So it's okay that you guys are making that mistake because it just takes some time to kind of get used to the fact that the exponent operation is going to change because of the fact that we're pulling it from the exponent down to the base level. Now, what do you know about e to the c? Just c. And it's no longer an addition, and now it's times, and it gets pushed in front of the variable because that's normally where we like to put our coefficient values. We can also drop the absolute value because we know plus or minus is going to show up, and that plus or minus will just get, we know c represents both positive and negative values, so we can let that plus or minus just be absorbed into that c. Okay, so y is equal to ce to the kt. So this is the equation that you're going to see a lot, where if you see anything in this form, a derivative equals to a k times the original variable, you know it's just going to end up looking like this. So from now on, if you see anything that resembles this, you don't have to go through the full integral process because you know it's just going to end up after you go through that step to be this. It may be a different variable, but if it has this pattern, we can jump from here directly to here. Okay. Now, if it doesn't look exactly like this, then we do need to spend the time to go through. But this is the most popular differential equation for these word problems. So this is the one you're going to see the most. Okay. So let's look at number 2 here. The rate of increase of population of a certain question. Yeah.
The C takes up the plus or minus. Right?
That's right. The C takes the plus or minus. So it does handle that. So we drop the absolute value, but we do it with a reason. Yeah. Okay. Number 2. The rate of increase of population of a certain city is proportional to the population. Look at the wording. It's very similar to number 1, right? Rate of increase of population. Let's think of that as P prime because it's a derivative involvement there. Is proportional. So you know it's going to be in the form of everything in the numerator here, y equals kx. And the last variable is population, which is just P. P prime equals Kp, y prime equals Ky. It lines up nicely. It's just that now our variable is P instead of y. So we don't have to go through this full process. I mean, we could, dp over dt equals Kp. We can separate the variables just like before, but we know this is going to lead us to this general equation that can be our starting point from here on out. Okay, so we're skipping all the calculus because we know that where this is going to lead. Okay, questions so far? Okay, if the population in 1930 was 50,000 and in 1960 was 75,000, what's the expected population in 1990? So a lot of numbers here. I like to organize this using order pairs. It just feels more structured and we can do the same thing every time. So I'm going to create order pairs. I know that time is my independent variable. I'm going to treat time as my x, and population is my dependent variable. I'm going to treat population as my y. So I'm going to set everything up this way. Time t being the x value and population information being the y value. Okay. It says if the population in 1930 was 50,000. So I'm going to use this information here. Now I could involve the years for time, but so that we can make things a little bit cleaner, a little bit easier for our problem, we're going to actually involve 0 whenever we can. So we're going to let 1930 be year 0. So let's say year 0, that's the earliest year that we see. Year 0, 1930, we have 50,000. Let's just build off of that, right? 1960, how many years after 1930 is that? 30. So that means 30 years later, our population is 75,000. What's the expected population in 1990? This is 60 years after our initial. 60 years later, we want to know what the population is. Now, the reason that we have so many order pairs here is because we have a lot of information that we need to resolve. We have this general equation. We don't know what the C value is. We don't know what the K value is. So the two order pairs is going to help us get to those information that we need to graduate this general equation to a specific equation with enough details to help us make this prediction. Okay. So typically we like to start with 0, because 0 kind of helps us take away a lot of variables and isolate information quickly for us. So usually whenever you see anything involving 0, this is going to help us find the C value, usually. And then what we're going to do is we're going to enter 0, 50,000 in for T and P. We're going to solve for C. And then once we solve for C, we're going to update the equation. And with the updated equation, we can continue to improve information about this equation using my second order pair. And the second order pair is going to help us find the K value. Okay. Once we find the K value, we're going to update the equation again. And once we have the C and K replaced with specific numeric values, then we can make our final prediction what the population is in 1990, 60 years after 1930. Okay, so first things first, let's involve 0. 0 is going to be the most helpful here. So we'll enter 0 in for T and 50,000 in for P into my general equation. Okay, let's try to clean this up here. What's K times 0 is just 0. What's E raised to the 0 power? Okay, good. It's 1, right? Not 0. Anything raised to the 0 power is 1. But it does wipe this out to be just 1, and our C is just the value that we see in front of us. So C equals 50,000. Okay, as soon as we have our C value, we're going to update our general equation because we have information to make it more specific now. So P is equal to 50,000 P to the KT. Okay, once we have our updated information, we're going to move on to our second piece of information. We have our second order pair. We can enter 30 in for T, 75,000 in for P, and that should allow us to isolate that K. Let's try that. Okay, our goal is to solve for K, but there are some things that we can take care of first. What should we do first? Yeah, let's get that coefficient to be cleaned up, right? That 75,000 and 50,000 can be resolved. Let's divide both sides by 50,000 just to get that cleaned up. Okay, use your calculator. What does that reduce to be? Okay, 1.5 or 3 over 2. I'm going to use 1.5. It's just fractional values tends to be a little uglier in terms of, especially when there's like exponents and fractions involved. So I'll use 1.5. It just feels a little bit cleaner, potentially down the road. This goes away. Okay, 1.5 is equal to e to the 30k. I'm still trying to solve for k. At least I have a simpler equation now. What's my next step? How can I handle a variable in the exponent? Yeah, so now we want to try to bring it down, right? Now we're trying to find a way to bring that exponent down, and a quick way to do that is involving natural log, right? We know natural log has nice properties that allows the exponent to freely move, depending on where we want it to go. So here we're going to take the natural log of both sides. So anytime we have a messy exponent that we want to try to have an easier time to work with, usually we want to bring it down. If we want to bring something down, there's no calculus here. We're just involving log properties. So we take the natural log of both sides. That 30k can free to move in front as a coefficient. Okay, so that 30k got brought down. A lot easier to work with a variable that is sitting at the base level rather than the exponent level. but what do you know about natural log of e? That just becomes 1, right? So that goes away. So now we have a cleaned up expression here. Natural log of 1.5 is equal to 30k. We're trying to solve for k. One last step is what? Divide by 30. Okay, so we now have the k value. We can update our equation down to as specific as we can make it. Now, we're going to hold on to our k value. I know it's tempting to just enter this into the calculator and get a decimal value, but we want to hold on to this because we want to improve the accuracy of our end approximation. So if we just use 3 decimal places here, it'll really influence the accuracy at the end. So even though it's messy, it will improve our accuracy. So we're going to hold on to this exact k value, and we're going to replace our updated equation with the new k value that we just found. Okay, so P equals 50,000, E to the natural log 1.5 over 30T. Now we have as specific as we can make it. We were able to use the 2 order pairs to find those 2 variables. And now we have enough information, enough things filled in where we can make a good prediction as to what the population is. So we can enter 60 in for T, and then we can solve for the population. And now the calculator can help us out here. Okay, so practice entering into the calculator with all the keystrokes and exponent and exponential function base E. Make sure you know where to find those. And we should get a number that's will represent the population in that year. Okay, the way you get E, yeah, it's next to, yeah, is that ln, second ln, next to 4. Okay, any questions with number 2? Okay, does anybody still need to look at number 2? All right, go ahead and turn the page. Number 3 is very similar setup. I just want us to kind of practice through the same steps as number 2, just to kind of feel more confident with everything that we've done. It's a lot of steps. It's not hard, but it's a lot of things that we need to put down, right? So go ahead and read number 2 and see if you can set it up very much the same way that you did with number 2. Yeah, page 6, number 3. Okay, I'll talk about it in a minute just to make sure that you guys are starting off on the right with the right steps, but go ahead and try it first. Everybody good with this page? Okay. So I provided some information on the board there. It says if 60 milligrams of radium are present now, and its half-life is 1,690 years, how much radium will be present 100 years from now? So the earliest time that we see is present day now. So we'll let 0 represent the time when there's 60 milligrams of radium. Okay. We know that 1,690 years from now is half-life. So that means 1,690 years from now, how much radium is going to remain? 30. And then it says how much radium present 100 years from now. Okay, so C. No, I think this is still the same. We can still use that 0 and 60 to solve for C, use this to solve for K. So it should feel very similar in terms of the steps that you took for number 2. Okay, so try that. See if you can look back at the steps and kind of take them on your own so that you can get comfortable with this process here.
Are you gonna take off points for like safe days? No.
Yeah, the only thing is just hold on to your K value. Don't approximate until the very end. So hold on to all your exact values, or hold on to your exact representation, and you should be able to get an accurate read on that approximation at the end. Okay, so here are the steps, right? We know that the 0 and 60 is going to be involved in helping solve for C. So T gets replaced with 0, 60 replaces R. We get that e to the k0 to become 1, so C equals 60. Once you have your 60, update your equation, and then continue with your second order pair. So we'll insert 1690 in for T, 30 in for R. And once you have that, 30 is equal to 60 e to the 1690k. I'm now focused on trying to solve for k, but one thing at a time. Let's move that 60 over to the left side, divide both sides by 60. 30 divided by 60 is 1/2, or 0.5. So next step, you have 1/2, or 0.5, is equal to e to the 1690k. Right, so now that you're sitting at that 0.5 equals e to the 1690k, you're now trying to find a way to get that K to be brought down at the base level to make it easier to work with. And we know natural log is going to help us get there. So we take the natural log of both sides, which now opens up that property that we have available under natural log to bring that exponent down. Once that exponent comes down, 1690K times natural log of E, we can make natural log of E go away. That's just equal to 1. Okay, divide both sides by 1690, and that is your K value that you want to hold on to. Take your K value, take your C value, update your general equation, and now you're ready to make your final step. Replace T with 100, and the rest can go in the calculator, and that can help us solve for R. Okay, any questions? Okay, one final one, number 4. We're still going to set up the same way, but the order that we're solving for the variables may be a little bit different here. All right. Everybody good with 3? Okay. Here's number 4. All right, so number 4 says, in a certain culture where the rate of growth of bacteria, so I'm going to call that B prime, is proportional to the amount of bacteria present. So it looks like I'm going to get the same format, right? B prime is equal to K times B. Okay, and we're only going to do part A here. Okay, we know it's going to be the same format, so B is equal to CE to the KT. That's our starting point. Right. You said it says the number is going to triple in 3 hours. Okay. So that tells us that initially, at let's say time t equals 0, there is some amount or number of bacteria. Initially, at time 0, there's some initial amount. We don't know what that amount is, but we know that is that amount is going to be associated with t equals 0. So we can create our structure or order pairs, right? Time being the X, bacteria being the Y. So we know that at time t equals 0, there's some amount, some initial amount. We'll just call it C, since we associate C with the initial amount. Now, second order pair says the number triples in 3 hours. So what order pair can we create? Yeah, 3 hours later, our number is going to triple, so 3C. Okay. If at the end of 12 hours, there are 10 million bacteria, instead of writing 10 million, I'm just going to write 10 to represent 10 million. And at the end, I'll just multiply my number with 1,000,000 just so I can get it back to my units here. So we have 3 order pairs, but we're going to have to do things a little bit differently here because if we plug in 0C, we're not going to make much progress. We're going to get the same equation here. So we're going to start off with another order pair here. We know that C is going to be the last thing that we find because that's what we're solving for. So we're not going to be able to make much progress trying to enter in 0C. So let's enter in 3C. Maybe this can help us solve for K. So we'll enter 3 in for T. We'll enter 3C in for B. Okay, the C's can go away. And then we can involve natural log just like before, because we're trying to get that exponent variable to come down.
So why does that natural log of E just go away?
Because natural log of E is equal to 1. Yeah, that's one of the properties. Because natural log is log base E, so log base E of E is just equal to 1. Yeah. Okay, so bring that exponent down in front. Divide both sides by 3. Sometimes I just like to rewrite that fraction as a coefficient. So I'm going to rewrite it as 1/3 natural log of 3. I'm going to update my equation. Don't have the C value because that's the last thing I'm going to be able to find. CE to the 1/3 natural log of 3t. Now, if I look, what if I insert that third order pair now? If I enter in 12 in for t and 10 in for b, that should allow me to get c being the only variable. And this should be enough for us to get back and solve for c. Okay, so we'll go ahead and enter 12 in for t and 10 in for b. Okay, we're trying to solve for c here. I can clean this up a little bit here. Careful that you don't multiply the 3 and 12 together, right? This 3 is inside the natural log. The 12 is a coefficient, but the 12 can merge with the 1/3, though. These are both, yeah, it's just 4. 12 over 3 is 4. And now we're close to the end because e to the 4 ln 3 is just a number. How can I solve for c? Yeah, just divide this whole value over to the left side. Okay, so 10 divided by e to the 4 natural log of 3. Enter that in the calculator. Keep in mind that we used a number that represent millions, so we need to multiply our result with 1,000,000 to get it back to the true number here. Any questions? Yeah. Yeah, so it's, yeah, this is already in terms of millions, so whatever number we get, I'm just multiply by 1,000,000.
Also, I did it where I just divided 10 million by 3.
Okay, did you get the same result?
Yeah.
Okay, you're good.
Can you move the paper up a little bit?
Sure. Okay, so we're going to pick up Monday going over slope fields. It shouldn't take the whole period, which will allow us to begin practicing a bit more with differential equations from 6.3. You guys have homework over the weekend. I'll send you guys a reminder Sunday. I know some of you guys didn't get a chance to finish the homework from Thursday, so I'll get a chance to kind of catch up. By 1,000,000. Because at the very beginning, yeah, at the very beginning, I had 10 to represent 10 million, so I don't have to deal with such large numbers. Yeah.